Okay, hello and welcome to our first lecture of this particular week. We shall keep going from the spot in chapter 6 where we left off. And that is, we've been talking about quantum mechanics and the development of the current model of the atom, which is known as the quantum mechanical model of the atom. The details of quantum mechanics can get quite confusing and very complicated. So we're trying not to get too deeply into it, but basically just deeply enough to give us an understanding of what atoms are like and how, and an idea also of how we know what they're like. Sorry. According to Niels Bohr, who we were talking about a little bit last time, with his Bohr model of the atom, which is also called the planetary or the solar system model of the atom, where you have the nucleus at the center, sort of like the sun at the center of the solar system, and then you have electrons going around, or revolving around. Sorry, the nucleus, sort of like the planets revolving around the sun. And there are a couple differences between the Bohr model and the solar system. Well, first of all, the solar system is a bit bigger, but anyway, one of the biggest differences is that in the solar system, all of these orbits of the planets are more or less in the same plane. There are one or two that are at a slight angle, but they're more or less in the same plane. The atom is actually three-dimensional. So these orbits can not only go around and around like this, but they can actually come out of the paper and go back in too, or any other angle, so that the atom is effectively a sphere. So each of these orbits might more accurately be called a shell, because the electrons are not only zipping around and around in the plane of the paper, but they're coming out of it and around in all different angles, forming, and they're moving really, really fast, so that in effect, they're forming kind of concentric shells around the nucleus. And so the first orbit would be called n equals 1, or the first shell would be called n equals 1, and then n equals 2, and n equals 3. This model of the atom is actually accurate for hydrogen. But when you get more than one electron, things, like I've said before, get a lot more complicated. And so the field of quantum mechanics was basically necessary to deal with anything other than hydrogen. Because we like to think of the electrons so far, at least the Bohr model did, of being sort of nice circular areas around the nucleus, or spherical, actually, technically, areas around the nucleus. But actually, when you get more than one electron, you get situations in which the electrons can be found in areas that are not spherical around the nucleus. And we'll get into that a little bit later. Also, there's a difference in that each of these orbits can accommodate more than one electron. And there are limits on how many electrons there can be in any given orbit. And it's related to the n number of the orbit, n equals 1, n equals 2, n equals 3. They have different limits on the number of electrons that can be in each orbit. Whereas in the solar system, there's generally only one planet per orbit. The planet might have a moon, but that, or more than one moon even, but that the moon would be much smaller and much less significant than the planet. The electrons, of course, are all identical to each other, and their energy is determined entirely by where they are relative to the nucleus. So you can have more than one electron per orbit. Bohr, as part of his theory, theorized that electrons behaved more like circular standing waves around the nucleus. And that for any given principal energy level, there can only be a certain whole number of waves that will fit around the nucleus. And that's sort of an explanation of why energy is quantized, because you can't have 4.5 waves, standing waves around the nucleus. You can only have 4, or you can have 5, but you can't have anything in between. So whole numbers only were allowed, and that is a good explanation of why, again, energy, like energy that's emitted in emission spectra, why it is quantized, and you don't get a continuous rainbow of colors out. You only get certain lines of certain colors. related to the fact of the standing waves. And a little bit later, Erwin Schrodinger came along and devised an equation to explain that situation, which is known as the Schrodinger equation. And it takes the form of H with a little hat over it, called a circumflex in French. I'm not sure if it even has a name in English other than little hat. But H with a little hat over it times the Greek letter psi equals E times the Greek letter psi. And we'll get down below here a little bit to what those things mean. But anyway, he was able to reproduce Bohr's results for the energies of hydrogen and hydrogen-like atoms. Remember, hydrogen-like atoms are basically any atom or ion that only has one electron. That would be a hydrogen-like atom or ion. This also agreed with the Rydberg equation. And so when you, basically when your new equation agrees with all kinds of stuff that already exists, that's a pretty good sign that you're onto something. And Schrodinger again concluded, like Bohr, that electrons are three-dimensional standing waves. Actually, Bohr didn't have the three-dimensional part. That was new with Schrodinger. But they're three-dimensional standing waves. Another term for a three-dimensional standing wave is a wave function. So it's a wave that doesn't move through space. It just exists in one place. Sort of like a guitar string when you pluck it. It vibrates up and down in place. It doesn't move longitudinally, along the length of the string. And the wave function is represented by the Greek letter psi. Another physicist by the name of Max Born interpreted the wave function as being not a physical wave, okay? Even though electrons are particles, the physical or the type of wave that he was thinking of is represented by psi, but it's not a physical wave. What it really does is psi, that is the wave function, represents the magnitude of probability. That is probability that an electron would be in a given spot in a given moment. And it so happens that when you take the wave function squared, then what you get is the probability of an electron being at any given spot at any given moment. And this is just the absolute value of psi squared, because the probability can't be negative. 0 is the smallest probability you can have. So so if psi squared comes out to be negative, well, you take the absolute value of it. And it can be used to map out the most likely locations for electrons within an atom. And so that's what we use to basically look at it, to map out electron configurations, to decide where the electrons are within an atom. It's the result. We don't actually use this directly, but we use the result of this equation as it's been mapped out over 3 dimensions around the nucleus of an atom by previous scientists. Now, the Schrodinger equation takes this form of H with the circumflex psi equals E psi. In this case, H with the circumflex is what's known as a Hamiltonian operator, and that's a complicated mathematical function that has to do with the energies of the electrons. And E stands for the actual value of the total energy of the electron. Okay, and so when they work all that out, you don't really have to know in detail what any of this stuff means, just that when they work all of this stuff out, it helps us devise where the electrons are likely to be around the nucleus of an atom and where they're not likely to be. Okay, so for understanding the quantum theory of electrons and atoms, the use of quantum mechanics, that is equations like the Schrodinger equation, allow us to basically come up with 3-dimensional maps of the most likely locations for electrons in an atom. But because of the Heisenberg's uncertainty principle, remember, we can't know exactly where an electron is at any given moment. The uncertainty principle says that we can either know the momentum of something small like an electron, or we can know its location with accuracy, but we can't know both of those things at the same time. And in practice, it's a lot easier to measure the momentum of an electron. And so it's the location that we can never know exactly. And as I showed, sorry, excuse me, in the last lecture, if you do the equation, if you use the Heisenberg equation for figuring out what is the uncertainty and location of an electron in an atom, you come up with a number that's about 10 times bigger than the entire atom. So that's a pretty big uncertainty. In other words, we have no idea where that electron is within that atom at any given moment. According, if you believe Heisenberg, the electron could actually even be outside the atom by quite a lot, actually. So what we do instead is we use Schrodinger's equation to map out areas where electrons are most likely to be at any given moment. It's a matter of like playing the odds. And so we can map out these areas. We can say electrons are most likely to be in these areas and not very likely to be in these areas, and sort of somewhere in between in the intermediate areas. So there's maybe, some chance of finding an electron in some areas, and in other areas there might be a very high chance of finding an electron there at any given moment, and in some places there might be no chance at all at finding an electron there at any given moment. But that doesn't mean that there would never be an electron there at any time ever. Essentially, looking at Heisenberg, according to his equation, the electron technically could be just about anywhere within the atom, even in the nucleus, at any given moment. But probably wouldn't be. You're not likely to find it there, but it's not impossible. Okay, so the areas where the electrons are most likely to be found are known as orbitals. And because this is a probability type of thing, the orbitals are not really sharply defined in space. We can represent them as if they are, but what we're really drawing out would be sort of the outer surface of the area that encompasses, say, a 95% chance of having the electron within it. But that would still mean there's a 5% chance that the electron could be somewhere else outside that area. So again, nothing is really definite. Everything is just kind of fuzzy and approximate. The areas where electrons are most likely to be found, orbitals in other words, have different sizes and different shapes for electrons of different energies. Particularly, they have different sizes based on the n number. So you'll have essentially the same shapes of orbitals in each principal energy level, but the bigger the number of the principal energy level, that is the n number, the bigger the orbitals will be. They'll be the same shapes as they are in the other principal energy levels, but they'll be bigger as n gets bigger. Okay. And again, as we've said before, but just as a reminder, the energies of electrons in an atom are quantized. That is, in other words, only certain values are allowed. And that has to do with the electrons having to be in these orbits that are at not technically not literally fixed locations, but the orbits can only exist within a certain range of locations, and that has to do with their energies. An electron can jump from one level to another, and that involves a change in energy. If the electron jumps to a higher energy, that is an orbit further from the nucleus, then the electron has gained energy. If the electron drops to a lower energy position closer to the nucleus, then the atom releases energy in the form of photons. Each transition involves the absorption or emission of one photon. Okay, and delta E would be the difference in energy between the final resting place of the atom and the initial place where it started out before the transition. The energy levels, and again, just this is a bit of a review, the energy levels in which the electrons are allowed to reside are identified by N, which so far we've been looking at as principal energy level. But now that we're talking quantum mechanics, this N becomes, well, it's still principal energy level or shell number if you prefer, but in quantum mechanics, it's referred to as the principal quantum number. But it still means essentially the same as what it's always meant. Okay, so that's not a big change. It's just a little change in the name. Principal quantum number is n, or shell number, if you will. The values allowed for n, again, are positive integers, 1, 2, 3, 4, and so on, counting out from the nucleus. The energy of electrons increases as n increases, but what that really means is that the energy of the electrons are getting less and less and less negative as you move away from the nucleus, with the maximum energy of the electrons being 0 at an infinite distance from the nucleus. The increase of the energies of the electrons with increasing value for n is not linear. There is a big gap between n equals 1 and n equals 2. And the gap between 2 and 3 is smaller, and the gap between 3 and 4 is smaller, and the gap between 4 and 5 is smaller, and the gap between 5 and 6 is really small. So actually, the principal energy levels, in terms of energy, they get closer and closer together as you move further out from the nucleus. N defined, that is the n, the principal quantum number, defines the energy and the location of the energy level. That is basically how big it is. But it doesn't tell you what the shape or the orientation in space of the orbital will be. That's coming in the future. N is also called, again, the shell number or the orbit number, as we've been calling it so far. The diameter or orbit of the shell also increases as n increases, but again, it's not linear. It increases pretty much like this. So the size or the diameter of n equals 2 is quite a bit bigger than n equals 1. N equals 3 is moderately bigger than n equals 2. 4 is, kind of bigger than n equals 3. 5 is only a little bit bigger than 4. 6 is only a tiny bit bigger than 4, and so on, and so on, and so on. Okay, figure 619 on page 306 or 316 shows you the relationship between the different principal energy levels. The transitions from one energy level to another can be viewed through quantum mechanics. For instance, for hydrogen, the change in energy of an electron undergoing a transition is just going to be the energy of the electron in its final location minus the energy of the electron that it had where it started out. EF minus EI, or E final minus E initial. And mathematically, that's given by the constant K, negative K, negative 2.18 times 10 to the minus 18 times 1 over n final squared minus 1 over n initial squared, n being the principal quantum numbers or the shell numbers, and F being the principal shell, or the shell number or principal energy level where the electron ends up, and Ni being the principal energy level where the electron started out. And that will give you the energy of the transition. From that, you can use the other equations that we've seen, E equals h nu or E equals hc over lambda, to find out what the frequency or the wavelength of the photons absorbed or emitted would be during this transition. If delta E is negative, this works sort of like thermodynamics. So if delta E is negative, that means the atom has released energy. In other words, the electron has fallen from a higher energy position further out from the nucleus to a lower energy position closer to the nucleus. And if delta E is positive, then just the opposite has happened. The atom has taken in energy or absorbed energy. Now, the electrons are actually located in certain areas within an energy level. That is the location where there's the greatest probability of finding an electron. It's not always spherical. For some electrons, the most likely area in which you would find them is a spherical area around the nucleus, but that's not always the case, not for all of them. And so again, the area where the areas within a principal energy level where you're most likely to find an electron would be known as orbitals. and there are different types of orbitals. Okay, and so that calls for another quantum number. This is known as the secondary quantum number or the angular momentum quantum number, and it is symbolized by a lowercase letter L. So lowercase letter L is the second quantum number, and what it basically tells you is the shape of the area of greatest probability for finding an electron. And most principal energy levels can have more than one type of orbital, more than one shape of an area of probability for where you're likely to find electrons. So the allowed values for L would be 0, 1, 2, anything up to n minus 1. So the maximum possible value for L would be n minus 1. And so remember, you can think of L, the secondary quantum number or the angular momentum quantum number, as being just an indicator of what shape or what type of orbital you're dealing with. And so if n equals 1, the only possible value for L would be 0, because 0 is the minimum value for L, and n equals 1 is the maximum value for L. But if n is 1, then n minus 1 is 0. So if n equals 1, then L equals 0 is the only number you can have for L. In other words, there's only one shape of orbital involved in the first principal energy level. Okay. If n equals 2, the value for L could be 0 or it could be 1. In this case, L equals 0 would be the same shape as the L equals 0 type of orbital for principal energy level number 1, except that in principal energy level number 2, it would be bigger. Same shape, but bigger. There's also the possibility that L could equal 1, and that is a new and different possible shape for an orbital. So if you're talking about n equals 1, there's only one shape of orbital possible. If you're talking n equals 2, then there are two shapes or types of orbitals possible. If you're talking about n equals 3, there are three shapes or types of orbital possible. So the number of different types or shapes of orbitals would be the same as the shell number or the principal quantum number. And that also means the the number of possible values for L would be the same as the principal quantum number. So if n equals 3, the values for L could be 0 or 1 or 2. That's three possible values for n equals 3. L equals 0 in n equals 3 would be the same shape as L equals 0 in n equals 2, and the same shape as L equals 0 and n equals 1. The difference would be the size and the energy. The size would be bigger and the energy would be greater, but the same shape. L equals 1 in the third principal energy level would be the same shape as L equals 1 in the second principal energy level. But the difference again would be the size or the energy. And L equals 2, that's a possible size or a possible type or shape of orbital that doesn't exist in n equals 1 or n equals 2. So you can only have that type of orbital starting with n equals 3. And then if you had n equals 4, then of course the values for L would be, there would be 4 of them, and the values would be 0, 1, 2, or 3. And so on and so on and so on. So each value of L denotes a different type or shape of orbital. And when you group together the orbitals of a given type, that is the orbitals that have the same value for L, you get what's known as a subshell. All right. Most types of orbitals, as it turns out, are present in multiple examples within any given principal energy level. So like, for instance, if L equals 0, there's only one of those in each principal energy level. But for L equals 1, there can actually be 3 of that type of orbital because of the shape of it. It allows 3 different orientations in 3 dimensions, and so on. And we'll get to that in a little more detail later. But what we mean by degenerate is that all of the individual orbitals of that type within a given principal energy level will have the same energy. Or basically, degenerate means that orbitals of the same size or energy and the same shape, but they have different orientation in space. So same size, same energy, they're just turned a little bit. The orbitals are also named with letters. That is, the orbital types are also named with letters. And that's the way they're actually best known. And that's the way that we'll be calling them most often. So I wanted to make sure to introduce those. The L equals 0 type of orbital is also known as an S-type orbital. There is one single S-type orbital in each principal energy level. That's what the 1 there means. And S, in this case, you can think of it as just standing for spherical. So S orbitals are spherical, and there is that what the squeezed in writing here says is that there's one of those for each energy level. For P, okay, let me get this up here. 308, 318. I will try to all right. For L equals 1, these are known as p-type orbitals, and there are 3 of those in each shell or each principal energy level, starting with n equals 2. So there are no p-type or L equals 1 orbitals in n equals 1, but every shell or every energy level from n equals 2 on will have this type of orbital, and there are 3 of them. And the way they differ is in their orientation in space. They're kind of a dumbbell shape, or depending on how you draw them, they can come out kind of looking like a figure 8 shape. And there are 3 of them because you're able to orient them along the X and the Y and the Z axis in 3 dimensions. Diagram 621 in the textbook is very useful for this kind of thing. It may look a little blurry on the screen, but you can get the idea of the shape of these. There is an S-type orbital. As you can see, it's spherical. And when you have a sphere, there's really only one way to orient it in space. You can turn it around, but it's still just a sphere, and it looks exactly the same as it did before. But if you have something like this, then obviously there are 3 different ways you can orient it. You could orient it along the x-axis, like it is here, or you can orient it along the y-axis like it is here, or you can orient it along the z-axis like it is here. And so that's px, py, and pz. And that's why there are 3 p-type orbitals in every principal energy level starting with n equals 2. All right. Now, the next ones are known as d orbitals. That is, if L equals 2, then that would be known as a d-type orbital. And there are 5 of those in any given energy level that has them, but they don't actually start until n equals 3. So there's no such thing as a d orbital in n equals 1 or n equals 2, but there will be d orbitals in all of the principal energy levels from n equals 3 on. And most of them, D's was where the shapes start getting fairly complicated. They're kind of X-shaped, and there are like 4 different ways that you can orient that. Plus, there's this other weird one that looks sort of like a donut stuck onto one of those long, skinny balloons. And that's for a total of 5 d-type orbitals in each principal energy level that has them. And for those, you can see those right here. 1, 2, 3, 4, 5. You can see that the first two and the last two have very, basically they're the same shape, and they just vary in their orientation in space. This is the different one. This is the one that looks sort of like a donut over a balloon or some weird thing like that. So that's kind of the misfit. But anyway, there are 5 of them, and they only differ with their orientation in space. Looking back here momentarily, if L equals 3, that's known as an F-type orbital. And there are 7 F-type orbitals in each energy level, starting with n equals 4. The shapes of the F orbitals are really complicated. Certainly, I don't expect you to know anything about the shape of those, but I'll just, you can see the shape if you look at that figure 621, and I will show them here. There they are. And as you can see, the shape is pretty complicated, but for the most part, most of them are pretty much the same shape. It's just the orientation that's different from one to another. And there are 1, 2, 3, 4, 5, 6, 7 of them, starting with n equals 4. And so that would be L equals 3. Okay, so the areas that are mapped out in that figure are basically the areas that are include about 95% likelihood of actually finding electrons within that area. So there is a small likelihood that you could find that type of electron beyond the bounds of the figures that were drawn, in that figure 621, but it gives you an idea of the most likely locations. But those electrons could be just about anywhere within that area. Figure 620 on page 307 or 317 gives you a map of the probability of finding certain types of electrons based on the linear distance from the nucleus. And you see that there are some areas or some locations where the probability actually does drop down to 0. So there's essentially 0 chance of finding the electrons in those areas. And then there are other areas where the electrons are quite likely to be found. And we tend to focus on the areas where the electrons are most likely to be found, and we consider that to be the location of those electrons. And the areas where they're maybe less likely to be found, but maybe not 0 probability, we tend not to focus so much on those, even though there is a chance that they could be there. Okay, we're well over time for the first segment, so I'm going to cut it there and come back with part B in just a moment.